So we have an issue where we have different methods where they have an optimal measurement range. So your Tmax and your compensation heat pulse methods are great at high flows, and your heat ratio method is great at reverse and zero and slow flows. So ideally we want a method that can measure reverse, zero, slow and high rates of flow. So a solution for this is to do what's called the dual heat pulse methods. And Pearsall et al. Did exactly this in their 2014 publication, where they combined the compensation heat pulse and the heat ratio method. So the dual pulse method basically means just combining two different heat pulse methods over their optimal range. And the reason why we can do this with confidence is because when you correlate two different heat pulse methods against each other, they more or less have a one-to-one correlation and very low scatter. So this graph over here, we see an example from Burgess et al. In 1998, where they compared the heat ratio method against the compensation method. And these data actually fall on a one-to-one line. And there's a couple of outliers there and there, but the scatter around that one-to-one line is very low, so the precision is very high. So we know that our different heat pulse methods are more or less exactly the same, even though they're calculating heat pulse velocity with different equations. The outcomes are very, very similar. Therefore, we can have confidence in switching between methods over their optimal ranges. So when Pearsall et al. Combined the compensation and heat ratio methods together, they found that their error improved. So they only had an error of 7%, and their precision was also very good. So they were getting R-squares of 0.97. So their configuration that they used looked like this. It was a 4-probe configuration, and you can imagine that it looks a little bit messy in this graph here, and in practice when you're out in the field, using a 4-probe configuration might be a little tricky. You can run into some installation errors with probe misalignment. There's also more wounding that you're inflicting on your plant, and not only that, but there's more temperature sensors that you need to measure, so you need to have more data logging capacity. What we advocate at Edaphic Scientific is a dual method where you combine the Tmax and the Marshall-Hogg heat ratio methods. So in this case, we have a 3-probe configuration, so you're minimizing any errors due to probe misalignment, but there's also less temperature sensors, so you can potentially add more sensors to a particular data logger, so there's less capacity there. And because you have less sensors, there is less cost involved as well. Or with the same cost, you can potentially increase your sample size or increase your replications. So we advocate the 3-probe configuration, combining the Tmax and the Marshall-Hogg heat ratio methods. So after you've measured your heat velocity, you want to go through and apply some correction factors. And the 3 main correction factors that you want to consider are probe misalignment, wounding, and thermal diffusivity. Unfortunately today we've only got 1 hour, so we don't have enough time to go through these various correction factors in details, but I highly recommend that you definitely consider all of them and that you should apply these correction factors to your data. So probe misalignment, for example, can be a huge source of error, and a great way to correct for that is to do the cut stem technique, which is what you see here. So we see some nighttime flows that are less than 0. That could have been reverse flow, but when we cut our stem, we see that the 0 flow offset is a consistent negative number, so then we can just shift our data set upwards. This electron scan down here is of a drill hole and wounding caused to a plant, and you can find this figure as figure 1 in Barrett et al. In 1995. So you can see here that there are loose fibers, there's a bit of tearing as well. So whenever we drill into a plant, we cause a lot of wounding, and so we need to correct for that wounding. The last correction factor you should really consider is thermal diffusivity. So you see a lot of papers, they just use a nominal value of 0.0025. And we highly recommend that you don't use a nominal value, that you actually use the various techniques that are out there to come up with your own value for thermal diffusivity. And again, if you have any specific questions or you'd like more information on any of these correction factors, please feel free to contact us at any time and we'd be more than happy to help you out. So after you've corrected all your data, you want to go from heat velocity to sap velocity. And Barrett et al. In 1995 provided this equation here. And again, we don't have enough time today to go through the specifics of this equation, but if you did want to go from your heat velocity to sap velocity, this is the way to go about doing it. The last step to do is to go from sap velocity to sap flow, and we give sap flow this value of Q. So it is a simple process of multiplying sap velocity by your conducting area. And conducting area could be sapwood conducting area, or could also be the leaf area that is distal to your sap velocity sensors. So whenever you're measuring these, and again, we don't have enough time to go through all the specifics of this today, but whenever you're measuring sapwood area or even leaf area, you want to make sure that you're doing it accurately, because a slight change can lead to big differences in your end values. For example, in this photo here of a tree stump, you might be able to see that the sapwood is quite different values around the tree trunk, so different depths over here, and here there's actually, down here there's virtually no sapwood at all. So if you just took one measurement in that tree, you would be getting a different value depending on where you measured. So it's quite important to do these things accurately if you want to get an accurate estimate of total sap flow and total plant water use. So I also just want to mention quickly about multi-point sensors. So again, we don't have enough time to go into any detail about this today, and if you do want to discuss this further, we're more than happy to talk to you at any time later. But one reason why I like using the heat pulse velocity sensors over things like your thermal dissipation or your heat balance techniques is because you can have multiple sensors along the same measurement probe or along the same sapwood radial profile. So in this case, we have the outer, middle, and inner sensors measuring at various points of the sapwood. And this can provide some very detailed information about plant water use and plant water relations or water use strategies. So if you are measuring particularly a very large tree, you always want to consider using multi-point sensors in order to characterize the whole sapwood in great detail and to get the correct information from your measurements. At Edaphic Scientific, we can actually provide the multi-point sensors for you. So here's an example of a heat pulse velocity sensor that we can provide that are manufactured by East 30 Sensors. So these sensors are low cost, so you can potentially get lots of these sensors for your data loggers. They come in a default configuration, or we can even custom design a configuration for your particular project. So the sensors are supported by Campbell's scientific data loggers, and in particular the CR1000 and the CR300 data loggers. We can also provide these data loggers for you, and we can pre-program them, so you don't have to worry about programming them. The SapFlow programs can be quite complex, and they can take a lot of time to write, but we've done all this for you already. Alternatively, you might already have your own Campbell loggers already. You might have a bunch that are sitting on the shelf, and we'd be more than happy to provide the sensors for you and even provide the programs and assistance with the programming. So with our programming, we use the dual methods approach, but you can adapt the program to any way that you want. So you're not stuck with using that one approach. It's highly flexible, and so you can apply it any which way that you want. We also provide free software to convert your delta T's to your heat velocity, your sap velocities, and your sap flow. So all those conversions are provided for you free of charge. And we can also provide environmental enclosures and solar panels and things like that as well. So it's all there for you. Lastly, we can collaborate on projects. So at the moment, we're collaborating on various different projects with researchers from all around the world. And collaboration could, be as simple as assisting you with designing your project and coming up with how many sensors you may need for your research grants, for example. Through to field installation or training your staff on how to install and manage the equipment, all the way to even data analysis and writing publications. So we do write publications with researchers, and we've got a few in submission as we speak. So the collaboration can be something as simple as you want, or we can really delve into an in-depth collaboration.